the effect of the species distribution modeling algorithms on the ecological niche of Ctenopisces courtesy.
Good afternoon, ladies and gentlemen. My name is Junhao Tu. I'm a master's student from Chongqing University in Taiwan. I'm honored to be here to present our study. The topic of our study is exploring the effects of species distribution modeling algorithms on the ecological niche of Ctenopisces courtesy. Chongqing University is located in Taichung in central Taiwan. And the Huisun Experimental Forest Station is also located in central Taiwan. That is our study area. I'll present our study in 5 parts, from introduction to conclusions. The prediction of species distribution has become a focus in ecology in recent years. We can use the ecological niche model to predict the potential habitat of species. On the other hand, when we build a model with different material or methods, we can obtain different types of predictive results. In this study, we want to explore the differences of predictions with different modeling algorithms. There are many modeling algorithms can be used in prediction, like classification tree, regression, profile method, and so on. Many studies have indicated that there is no best model. Instead, the best model will be decided by the objectives of study. On the other words, the prediction with different methods will be suitable for different applications. Every modeling algorithm is based on different principles. Therefore, the model with different algorithms will generate different type of prediction. In this study, we want to explore the differences of the predictions and evaluate which applications the predictions can be used in. The test target species is long-lived chinkpin. I'll call it LLC later. It grows widely in South China and Taiwan, and it's a sunloving tree, and its seeds are an important food source for many animals. The objectives of this study were to evaluate the differences among predictions for modeling algorithms, including max-n, GAP, SVN, and DT. And we also want to explore the relationship between the modeling and the predictive ecological niche, and to evaluate which applications each algorithm can be applied in. The study area encompasses the Huisun Forest Station in central Taiwan. The tree species over there is very complex. The range of altitude is from 450 to 2,400 meters. We took a tree sample from the east Dongfeng watershed in the east of Huisun area and extrapolated the potential habitat to entire study area. The data we used include orthophoto map, DEM, and spotlight images, and then derive the altitude, slope aspect, turn position, and the vegetation index respectively. The tree samples were acquired from field survey. Then we overlaid this data and input them into max-n, GAP, SVN, and DT4 models to predict the potential habitat of LLC, and validate the model by using independent samples in final. This map was derived from the DEM we used. The yellow part is the Huisun area. We use the DEM to derive altitude, slope, and aspect layers. and combined with the ridge and valley information that derived from orthogonal maps to generate the terrain position layer. And the vegetation index was derived from two spot images. One was acquired in summer in 2004, and another one was acquired in autumn in 2005. We established the vegetation index based on the principle of the changes in leaves moisture content in different seasons. Show us this equation. The tree samples were acquired by using GPS. The error will be below 1 meter. The number of tree samples which we took is 120. 2/3 of them were used to establish the model, and one-third of them were used in model validation. The background samples were randomly taken from entire study area. The number is 5 times more than target samples. Then we overlay these layers and clip it by the tree samples to obtain information about each factor in the position of tree samples. The first method we used is MaxN. It based on the entropy in thermodynamics and Bayesian statistics. It will find out the probability distribution that occurs most probably in nature. That is the value of maximum entropy. It calculates the maximum probability of presence in every pixel, then predict the potential habitat by adopting an appropriate threshold. Second method is GAP. It uses the genetic algorithm to pick out a best rule set for discriminating two classes. There is some best rule in the model. They will be selected and evaluated the adaptation. Then it will combine some rules in the evolution algorithms to generate some new rules. Repeat this step and output an optimal rule set for the prediction. Third one is SVM. It classifies the data by finding a hyperplane that can discriminate two classes most significantly. If they cannot be split linearly, they will be projected into a high dimension visual space to find a new linear condition to split two classes. The fourth is DT. It is a non-parametric classification technique. It classifies the data by sequentially dividing the data set into each class with some important variables until classifying completely or reaching the user set limit. In the step of model validation, the approach we use is split sample validation, and we calculate the overall accuracy and kappa coefficient to evaluate the accuracies of 4 models. In the result, the first table shows the accuracies of 4 models. All the kappa value of 4 models were higher than 0.8. It means that all these 4 models have strong predictive ability, and the accuracies of DT is slightly higher than other 3 models. This map shows the potential habitat of 4 models. The outputs of MaxN and GAP are gradient distribution, show the potential habitat from low to high probability of presence. SVN and DT are binary output. They only show the potential presence and absence. Max and predict the habitat based on the probability distribution. It predicts a habitat with high probability over the target samples than that over the background samples. And the result of GAP is also show us gradient distribution. The software we use desktop GAP was more on the omission errors, so it usually have wider prediction than other models, and it may be cover more potential suitable area. Both method and GAP2 method can also be used in different applications with different thresholds. SVN and DT identify the habitat by dividing the samples of two classes. They usually have clear boundary between two classes. More complex on the data, more concentrated and fragmentary on the area of predictive habitats, as shown here. And the predict habitat of DT is much more concentrated. It classifies the data by some sample rules. These two classification methods consider a background sample as the percent and split them from target samples as completely as possible. But on the other hand, they can still be used to find some area that is more similar to target samples. The area will have much higher potential for species survival. In final, we have some conclusions. And in these four models, the accuracy of DT is slightly higher than other three models. But it doesn't mean that it will be most consistent with the real world. It only means that it is most consistent with the existing samples. Instead, we must choose an appropriate method according to the goal of study. For example, if we want to find the restoration site of rare species, we can choose the classification method like SVN and DT. And if we want to find all the suitable environments of species, we can use the mass and GAP or profile method. And the gradient distribution method like Mason and GAP can also be used in more applications with different thresholds. There are still many algorithms can be efficiently used in predictions of species distribution. The applicability of each algorithm must be tested, and we also have to choose an appropriate method according to the goal of study to get a best results. That's all my presentation. Thanks for your attention.
So let's open for the question and the comment. Any question from the audience? Okay, I have a quick one. So you said the accuracy of the DT is much better, right? In your conclusion, slightly better. So how do you how do you validate your result? How are you so sure that the accuracy of the DT is better than others?
It just in this case, if in other case I didn't show whether it will be the best. But the accuracy of this four model is very close, so it just slightly.
The difference very small.
Very small.
Okay. See. Cool. So. So any other question? Okay, so if there's no more question, we can move to the next speaker. Okay, thank you.